You're here because you want to master the extraction of metals and rusting of metals with a University of Cambridge graduate. This is actually part 3 of our reactivity series lecture videos. If you want to check out the previous videos in this series, be sure to check out our playlist in the link below. And also do make sure to check out our video all the way to the end because I'm giving a summary of the reactivity series content. Hi, I'm Brendan and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. Previously, we have already covered displacement reactions of metals and how you can predict whether metals will actually get displaced based on their position in the reactivity series. We have also discussed about the thermal stability of the compounds and how you can predict their thermal stability based off their position in the reactivity series. So far everything has been using the reactivity series. Now we're going to talk about a different kind of reaction, right? Let's talk about the reduction of metal oxides by the metal. So a metal that is more reactive in general, right, will reduce oxides of less reactive metals that are lower in the reactivity series. For example, because zinc, right, is more reactive than copper, zinc can actually help to reduce the oxide, okay, and zinc will actually become zinc oxide and the copper will come out. This is kind of like a pseudo displacement reaction if you think about it. So I talked about this because we need to talk about the extraction of metals next. In general, your metal ores are usually oxides, okay, sulfides or carbonates mixed together with other impurities. What you want to do is you want to actually extract the pure metal out for several other purposes that you can use industrially or in day-to-day life. So to do that, right, you want to categorize the method of extraction first. In general, there are two methods of extraction. One is either electrolysis of the molten ore, or two, you do a reaction of the metal ore with carbon, which is coke, or carbon monoxide, or hydrogen. Okay, the method of extraction really depends on, you've guessed it, where the metal is on the reactivity series. So if you look at this table below, right, the reactivity series goes from top, where the metal is the most reactive at the top, and all the way to the bottom, where the metal is the least reactive. The metal, when it is more reactive, right, like potassium, sodium, calcium, magnesium, and aluminium, these reactive metals must be extracted via electrolysis of the molten ore. Okay, and this is where you pass an electric current through this molten compound. So if the metal is less reactive, for example, if it's a moderately reactive metal like zinc and iron and lead, or if it's really at the bottom of the reactivity series like copper and silver, right, the metals, okay, if it's moderately reactive, you can reduce it with hydrogen, carbon, or carbon monoxide. And if it is very unreactive metal, you can actually heat the metal oxide with also coke, carbon. Let's talk more specifically about the reduction of your metal oxides with hydrogen, carbon, or carbon monoxide. Generally, okay, the more reactive a metal is, the more stable is its oxides. And the oxides of highly reactive metals are not easily reduced to the metal. But for less reactive metals, right, that form oxides, these are generally more unstable, so you can reduce them more easily. Okay, so metals below carbon, in general, these are zinc, iron, tin, and lead. These in the reactivity series are extracted by the reduction method. Okay, and the more reactive the carbon, right, it is able to actually reduce the oxides of these metals. For example, lead can actually be extracted by reducing your lead-2 oxide with coke or carbon. Alright, and it follows this reaction where lead-2 oxide works with carbon to form lead and carbon dioxide. Beforehand, you actually had to memorize the whole extraction process with using the blast furnace and all that, but now we don't really need to because it's not in the syllabus. Your hydrogen, carbon, and carbon monoxide, these are all reducing agents, alright? And these are actually also arranged in increasing reducing power, where hydrogen is the least powerful reducing agent, followed by carbon, and then carbon monoxide is the most powerful reducing agent. If we look at the next table, we'll come to realize a table that can actually categorize the extraction method used based off the metal and its position in its reactivity series. So, as we've already discussed, your potassium, sodium, calcium, magnesium, and aluminium, because they're above carbon in the reactivity series, right? These metals are so reactive, right? And because the metallic ions form strong ionic bonds with the oxide ions, they cannot really be reduced with reducing agents like hydrogen, carbon, and carbon monoxide. So you have to use electrolysis to obtain these metals from their molten oxides and salts instead. Your zinc, right, can be extracted by using zinc oxide, and you reduce it to zinc, okay, with carbon or carbon monoxide over here. Okay, and in general, you cannot reduce it via hydrogen because I guess zinc is a more reactive metal comparatively, okay, and therefore you cannot use such a weak reducing agent like hydrogen. Next up is your iron, lead, and copper. These can all be reduced by your hydrogen, carbon, and carbon monoxide, okay, to extract these metals out. So here are all the equations over here. Your copper oxide, your lead oxide, your iron 3 oxide. These can all be extracted with either hydrogen or carbon monoxide, right? And you can get the pure metal out. Your mercury and silver, on the other hand, right, these metals are very unstable. So you can actually easily decompose them by heat or light to give the pure metal, right? You don't really need a reducing agent in those cases as well. For example, mercury oxide can decompose to give mercury. Lastly, all the way at the bottom of the reactivity series, you have your gold and your platinum. So these are just super unreactive metals, and it's usually found in its elemental state in nature. Now, let's talk about rusting. So the rusting of metals is actually the slow oxidation of iron, specifically, to form rust, a brown solid. Okay, and rust is actually hydrated iron 3 oxide, okay, where X over here in this formula actually indicates the number of water molecules surrounding each unit of iron 3 oxide. So part of the rusting conditions, which you have to memorize, okay, is oxygen and water. So if we know this, we can easily prevent rust from forming. And how do we do this? Well, we can either take out the oxygen or take out the water. So you can stop or slow down rusting, okay, with water and air being prevented from coming into contact with the surfaces of iron. Generally, there are two ways, all right? The barrier method and the sacrificial protection method. So the barrier method, as its name suggests, is just a way to form a barrier around the metal so that it doesn't come into contact with oxygen or water. So for example, if we cover the iron surface with oil or grease, right, this oil or grease is going to prevent air and water from reaching the iron surface. And examples of this is used in machines such as engines and bicycle chains, where they actually just put a layer of oil, okay, or grease, and you can definitely lengthen the lifespan of iron itself. You can also do painting of the iron surface. So by painting it, right, the layer of paint is going to prevent air and water from reaching the iron. This is mainly used in cars, iron railings, ships, and bridges. And lastly, okay, you can also do coating with another less reactive metal. If you coat with a less reactive metal, right, this prevents air and water from reaching the surface of the iron. Okay, but of course, if the surface is scratched, the rusting is still just going to occur. So this is usually used in cans and in canned food industries. Next, let's talk about sacrificial protection. And this is actually a very, very commonly tested method in the exams. So you have to understand the principle of sacrificial protection. If you put the iron or steel in contact with a more reactive metal, the more reactive metal will corrode instead of the iron or steel. Again, this makes use of the reactivity series. Alright, so for example, blocks of magnesium are actually attached to your underground steel pipelines, okay, by an insulated electric cables. And this makes the magnesium corrode in place of the steel pipelines. Okay, another example is your blocks of zinc, okay, that are placed on the hulls of ships. Zinc is more reactive than iron, so zinc is going to corrode instead. Alright, so by knowing the position of your metals in the reactivity series, you can tell whether sacrificial protection will work or not. An important tip that you have to know, okay, for sacrificial protection, you don't need to cover the whole metal with the sacrificial metal. You just need a bit of physical contact, okay, or via a wire. That's all you need. It's not like the barrier method where you have to use grease or paint, alright, to cover the entire surface of the metal itself. And that's actually the end of the reactivity series lecture videos. Now, At the end, there's also a summary which I've left behind of a lot of the reactions that we've kind of run through in our previous lecture videos. So you can go and read this summary tables to get a rough understanding, or you can use it as just a very quick revision before your exams as well, right? So here we have the summary of reactions of metals with cold water, steam, and acid, all side by side, right? In general, remember your more reactive metals, alright, will just have a more violent and vigorous reaction compared to the less reactive metals. However, you still have to memorize specifically which metals react and how do they react actually from the observations. And next, we have also the summary of reactions, okay, of your metal oxides with hydrogen and carbon, and also the action of heat on the metal carbonates. So this is what we covered under the reduction of your metal oxides using hydrogen and carbon, and also talking about the thermal stability of your metal carbonates itself. So again, this is just a recap on what we just covered as well. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.